Okay, so in the previous lecture, we had given a set of equivalent statements, which was which was used to characterize the concept of diagonalization of a linear operator, or you can say of a matrix. So let's just continue from there. So the set of equivalent statements was, it was indeed proven if we have those certain properties, then the matrix is diagonalizable. Let me just come up to this. So we had this set of equivalent statements that let T be a linear operator on a finite dimensional vector space V. Let C1, C2 till Ck be the distinct eigenvalues of T, and let Wi be the null space of the transformation T minus Ci times the identity operator I. That is typically saying that Wi is the eigenspace associated with the eigenvalue C. Then the following are equivalent. That is, T is diagonalizable. The characteristic polynomial of T is of the form f equals to x minus c1 to the power r1, x minus c2 to the power r2 till x minus ck to the power rk, with dimension of each eigenspace Wi equals to Ri, which is the algebraic multiplicity of the eigenvalue Ci. And number 3 was the dimension of W1 till dimension of Wk. If I sum over all these dimensions, then I get the dimension of V. And the essential discussions of the previous lecture was that if technically if 2 and 3 hold, then 1 is true, right? So in this lecture we start with an example showing that if T is diagonalizable, then these properties hold trivially. Let us come back to that. So suppose T is a diagonalizable operator. Okay. Suppose T is diagonalizable. Okay, suppose T is diagonalizable. Then, so if T is diagonalizable, then we have an ordered basis, right? Then for a certain ordered basis, say B given as alpha 1, alpha 2 till alpha n, we have T as that T of each alpha I must be equal to some constant Ci times alpha I, and this happens for all I equals to 1 to n, right? So this definition obviously implies that the matrix of T with respect to B is a diagonal matrix with the diagonal elements formed as follows. So it comes as, say, some C1 times the identity matrix I1, C2 times the identity matrix I2, and so on till some Ck times the identity matrix Ik, where the dimension of each of the identity matrix, say I subscript I, is di, and the sum over these di's eventually give you the dimension of the matrix, that is dimension of the vector space, which is n. Now we have considered such a representation to ensure that the repetition of these constants or the scalars Ci are considered. Okay, that is the goal behind this representation is, suppose you had the matrix of this form. Say suppose you had C1, C1, C2, C2, C3, C3, right? So obviously the way to write this is C1 times 1 0 0 1 in the diagonal. Obviously this is also 1 0 0 1, and C3 times 1 0 0 1, and the dimension of these identity matrices, they give you the algebraic multiplicity of each Ci, right? Or the repetition of each Ci as roots, or repetition of each Ci with respect to the values alpha i's present in the ordered basis completely, right? So this is why we have ensured such a representation. Observe that if T has such a representation, then the characteristic polynomial of T of the matrix of T with respect to the basis is of the form x minus c1 to the power d1 till x minus ck to the power dk. And since we have already considered the repetition of these elements, so each c1, c2 till ck are distinct, right? Where each c1, c2 till ck are distinct scalars. Now, since this is the characteristic polynomial, so obviously each of these c1, c2 till ck are the distinct eigenvalues, right? So let me just write it as 1. Since 1 is the characteristic polynomial, therefore each ci are the distinct eigenvalues of each ci are the distinct eigenvalues of t, right? Moreover, observe that when you are given the matrix, suppose this is the matrix A, okay? Or rather, since this is a diagonal matrix, let me use the notation D. Right. Now, what is D minus Ci of any column vector x equals to 0? What can we say about this system of linear equations? Observe that when you have D minus Ci, or rather, let me just come up with an example to have a better grip on this thing. If you consider this matrix D minus C1i, then observe that the first D1 rows becomes the 0 rows, right? Has D1 0 rows, right? So that means the nullity of the matrix D minus C1i is exactly D1, but that must be equal to the dimension of the eigenspace W1. But W1 is by definition the set of or the collection of all eigenvectors associated with the eigenvalue C, right? And this was indeed what we wanted, right? Therefore, D minus Cii, the nullity of this is equals to Di, right? And which is equals to dimension of W1. So observe that dimension of W1 so on till dimension of Wk is equals to D1 plus D2 and so on till Dk, but that must be equal to n from the given matrix representation, right? So therefore, if it's a diagonal matrix, if we are given a diagonalizable operator, then the statements in the set of equivalent statements given in the previous lecture, they automatically hold. Thus, we have actually concluded a very specific characterization of a matrix being or a linear operator being diagonalizable. I had used the terms of algebraic multiplicity and geometric multiplicity, that if you have a certain, if you get hold of a certain eigenvalue, then check the multiplicity of it with as a root of the characteristic polynomial, that gives you the algebraic multiplicity, and the nullity of the, or rather I should say the dimension of the eigenspace, which is given by the nullity of a matrix of this form, gives you the geometric multiplicity of that very eigenvalue. If the algebraic multiplicity and the geometric multiplicity are equal, that is certainly if this condition holds, because observe Di is the algebraic multiplicity of Ci respectively, right? So if this condition holds, that the algebraic multiplicity of an eigenvalue equals the geometric multiplicity of an eigenvalue, then by the equivalent statement I had given, it would conclude that the linear operator is diagonalizable or the matrix is diagonalizable, right? So before moving on, let us consider a simple example. So let us consider the, okay, let T be a linear operator on the finite dimensional vector space R3, okay, and let the matrix of T be given as, or rather let me just write it as A, because we are not concerned about considering any arbitrary basis as well, just to keep low of the notations we use in this example. So let A be the matrix, so it's 5 minus 6 minus 6 minus 1 4 2 and 3 minus 6 minus 4 be a matrix representation be a matrix representation of T with respect to some ordered basis of V. Okay. Now our goal is to check whether A is diagonalizable or not. Whether A is diagonalizable or not. If so, that is, if it is diagonalizable, find its diagonal form. Okay, so let us check this. So solution. Okay. So the first thing we have to do is we have to find the eigenvalues of it, right? So to find the eigenvalues, we need to consider the characteristic polynomial. So let f(a)x be the characteristic polynomial of A. Then by definition, we have f(a) of x to be given as so it's given as determinant of xi minus A. You can use, see, obviously we can use A minus xi, determinant of this, or determinant of xi minus A, because if A is an n cross n matrix, then A minus xi is also an n cross n matrix. So we can write A minus xi, determinant of this, as minus 1 to the power n times determinant of xi minus A. But since we want to equate this to 0, so this factor of minus 1 to the power n doesn't make an issue, right? Considering this actually helps because the factors of, I mean the terms where x is there inside this matrix xi minus A, x consists of a positive sign, right? So that's the only reason we consider this. Okay, so xi minus A, so that is exactly this matrix, right? So this is the matrix. So x minus 5, right? Then you have 6, right? Then you have 1, x minus 4, minus 2, and you have here minus 3 plus 6 and x plus 4, right? X plus 4, right? So this is the matrix you have. Now if you find the determinant of it, I'm not doing that. If you find the determinant of this matrix, so it comes out to be x minus 2 whole squared times x minus 1. Therefore, the eigenvalues of A are 2 and 1 with their algebraic multiplicities being 2 and 1 respectively, right? So our concern is to check whether the geometric multiplicity or the dimension of the eigenspace associated with the eigenvalue 2 is equal to 2 or not, and analogously the dimension of the eigenspace associated with the eigenvalue 1 is 1 or not. That will help us in understanding or concluding the fact that whether the matrix is diagonalizable or not. Okay, so let us go to the next page. Okay, so consider the matrix A minus 1i, right? That is exactly the matrix. So you have A minus 1i, so it's the matrix 4 minus 6 minus 6 minus 1 3 2 3 minus 6 minus 5. So the first thing we need to do is that we need to bring it to its row reduced echelon form, right? So let us come up with that. I'm not writing that in details. What we are doing is we are first shifting the second row to the first, or rather I should say we are replacing or interchanging the row 1 and row 2. So we have minus 1 here, 3 2 4 minus 6 minus 6, 3 minus 6 minus 5, right? Then we are multiplying the first row with -1 to get 1 minus 3 minus 2, and the rest of the rows are as it is, 3 minus 6 minus 5. Then what we are doing is we are subtracting the second row from 4 times the first row. Okay, so we are actually, what are we doing? We are, so r2 dash is equals to r 5 times r, sorry, 4 times r1 minus r2. So we have 1 minus 3 minus 2. So 4, so this becomes 0. Here you have 12, right? 4 times minus 3 is minus 12 plus 6, so it becomes minus 6. And 4 times minus 2 gives you minus 8, so this becomes minus 2, right? And here you have 3. And what we do is we, for the one more action we take, consider here, we are, so r3 dash, the third row is being written as 3 times r1 minus r3, right? So we have 0 here. So you have 3 times minus 3, so it becomes minus 3, and minus 6 plus 5, right? So you have minus 1. Now observe that if you just, subtract, so if you do this, that you have r3 dash now as r3 double dash, let's say, as r2 dash minus 2 times r3 dash. That is, we are subtracting the third row, the now third row, from the 2 times the now third row from the now second row. So we have 1 minus 3 minus 2, 0 minus 6 minus 2, and then you have 0, 0, and 0, right? And there cannot exist any more 0 row. You can obviously find it out from the structure of the matrix. And obviously we don't need to reduce it further, right? Because we have got a 0 row, and we know that even if we come up to the exact row reduced echelon form of this matrix, we won't be able to get any more 0. So this, manipulating this till this step will do, right? Therefore the nullity of the matrix A minus 1 times I is equals to 1, which is exactly equal to the algebraic multiplicity of the eigenvalue 1. Okay, so the first thing we have in hold is this. Now we need to do the same step for the second one, right? So let's check it out. So consider the matrix A minus 2i. So what is the matrix A minus 2i? So it's 3 minus 6 minus 6 minus 1 2 2, and then we have 3 minus 6 minus 6. So the first thing, which is very trivial to get, is if you just subtract the third row from the first row, right? So you get minus 1 2 2 0 0 0. Next you can do is you just subtract, you just add the second row 3 times the second row to the first row, right? So you have 3 minus 6 minus 6, you have 0 0 0 and 0 0 0, right? So you can get no more number of non-zero rows. Therefore the nullity of A minus 2i is equals to 2, which is exactly equal to the algebraic multiplicity of the eigenvalue 2. And this was what we actually needed, right, to check whether the algebraic multiplicities and the geometric multiplicities equate or not. Thus the matrix A is diagonalizable. Now we need to check that, or we need to find the diagonal form, right, or whether we need to find the diagonal matrix associated with this. So check the following. So to find the diagonal matrix, what we actually needed to do is that we need to find the basis of each eigenspace, right? Our goal is to find the basis of the eigenspaces say W1 and W2, where W1 is the eigenspace associated with the eigenvalue 1, and W2 is the eigenspace associated with the eigenvalue 2. So the typical observation from here is that since we know that the dimension of Wi is 1, so it's a span of a single element. So basis consists of only one element, right? So any one eigenvector we come up associated with the eigenvalue 1 will do, right? And in the case of the W2, so it will have a basis consisting of two elements. So we need to get, because the dimension of W2 is 2, so we need to get two linearly independent eigenvectors. How to solve for eigenvectors? That is also pretty trivial, because we know if alpha is an eigenvector, then A minus, so we know if alpha is an eigenvector associated with the eigenvalue C, then alpha must satisfy the following condition, right? That A minus Ci times alpha is equal to 0. So thus we can actually, what we do is that we have hold of these eigenvalues, so we can consider this as a system of linear equation, or simply as a matrix equation, and solve for this vector, right? So we go to the next page. So let xy belong to W1, then A minus I times the column vector xy must be equal to 0, 0, right? Right. Now, what was A minus I given to us? So A minus I, we had come up with the following, right? We had come up with the, yeah, so it's 1 minus 3 minus 2, 0 minus 6 minus 2, 0, 0, 0, right? So it's 1 minus 3 minus 2, that implies to 1 minus 3 minus 2, 0 minus 6 minus 2, 0, and we have 0, 0, 0. So this equals 0, 0, 0, right? Okay, sorry, I've done mistake. Yeah, this should be three-dimensional, right? Sorry. So we would need three ones. So x1, x2, x3, right, belong to W1. So here you have x1, x2, x3. You have 0, right? So times you have x1, x2, and x3, right? Okay. So from here it's obvious that x3 is a free variable, right? x3 is a free variable because it corresponds to a non-zero row. So x3 is a free variable. So we need to just find the values of x2 and the values of x1 with respect to x3. So what are the conditions we have up here? So notice that minus 6x2 minus 2x3 is equals to 0, but that implies 3x2 is equal to x3. So this is one condition we have, and the next condition we have is that x1 minus 3x2 minus 2x3 is equals to 0, but 3x2 can be written as x3, so x1 minus x3 minus 2x3 is equals to 0, but that implies x1 is equals to 3x3. So we have the following two conditions. So we just consider x3 to be an arbitrary value. So what can we consider x3 as? So suppose x3 is 3. Okay. Is it okay? Have I done a mistake? Yeah, it should be minus x3. Correct. Yeah, this should be minus x3. Right. Have I done any other mistake here? Let me just check it once. Yeah, because, oh yeah, correct. So this will become plus, right? This will become plus, right? Yeah, so this becomes x3, x1 equals to x3. Yeah, so these two things we get, correct. Therefore, let x3 be equal to 3, then we have x2 equal to minus 1 and x1 equals to 3. Therefore, alpha equals to 3 minus 1 3 is a basis element of W, right? Because it's spanned by a single element, so one single element will do. Is it clear? So let us come up with a similar procedure in case of the W2, right? So obviously, if some, let's say some gamma belongs to W2, then A minus 2i times gamma must be equal to 0. So we will obviously go up with this matrix equation only. So just let gamma be again equal to say x1, x2, x3, and we had A minus 2i as, we just come up to the previous page. So we had this as 3 minus 6 minus 6 and the rest are zeros, right? Right. So we have here 3 minus 6 minus 6, 0, 0, 0, 0 times x1, x2, x3, which is equal to 0, 0 and 0. Now obviously that we can write this equation like this as well, because we can just cancel out 3 from the first row of this coefficient matrix A. So we can write as a 1 minus 2 minus 2, 0 times the column vector x1, x2, x3, and we have here 0, 0 and 0. So now notice that x2 and x3 both are free variables, right? x2 is a free variable and x3 is a free variable as well, right? And we had x1 plus 2x2, x1 minus 2x2 minus 2x3 is equals to 0. So therefore we can write x1 as 2x2 plus 2x3, right? Right. So what we do is that, so let x2 be equal to 1 and x3 be equal to 0, right? Then x1 is equals to 2 and we get the following vector. Let's say alpha 1 equals to, so x1 is 2, x2 is 1 and x3 is 0 belonging to W2. And on a similar basis we choose x2 to be 0, x3 to be 1, and eventually x1 comes out to be 2 as well. And this vector we consider this as alpha 2, so it's 2, 0, 1, right? And this also in W2. Okay. So we have two vectors, two column vectors, 2, 1, 0 and 2, 0, 1 in W2. Observe that alpha 1 and alpha 2 are linearly independent. Therefore, since dimension of W2 is 2, alpha 1, or we can consider alpha 1, alpha 2 constitutes the basis of W2, right? Constitutes the basis of W2. So we have got hold of two bases, right? So BW1, let's say, so it comprised of the set 3 minus 1 3, right? So we have 3 minus 1 3. Then we have BW2, which consists of the vectors. So we have 2 1 0 and 2 0 1, right? Further, since dimension of W1 plus dimension of W2 is equals to 3, which is exactly equal to dimension of R3, therefore the basis B consisting of these elements in order, obviously in order, that is, so we have the elements as 3 minus 1 3, 2 1 0 and 2 0 1. So it constitutes a basis of R3. Okay, it constitutes a basis of R3. Okay, that's pretty obvious. Now observe that if you consider P to be this matrix, so we just put each of these basis elements in along the column. So we have 3 minus 1 3, 2 1 0 and 2 0 1. Right? Why are we doing this? If I just give a quick recap of what we discussed in the previous lecture, recall that if P is a matrix which consists of the elements alpha 1, alpha 2 and alpha 3 along the columns, I'm just using a three-dimensional example. So we have alpha 1, alpha 2 and alpha 3 as columns, which are eigenvectors associated with eigenvalues, say C1, C2, C3, not necessarily distinct. Then what is AP? Then AP is nothing but A times alpha 1, A alpha 2, A alpha 3. But A alpha 1 is nothing but C1 alpha 1, because alpha 1 is an eigenvector associated with the eigenvalue C1. Right? So you have so we have here C2 alpha 2 and C3 alpha 3. But this is nothing but alpha 1, alpha 2, alpha 3 times the diagonal matrix C1, C2, C3. Right? So we will obviously be doing that only. Then, so what is AP? So AP is the matrix multiplication. So we have 5 minus 6 minus 6 minus 1 4 2 3 minus 6 minus 4 times we have 3 2 2 minus 1 1 0 3 0 1, and by this fact this obviously comes up with P times the diagonal matrix, where the diagonal consists of the eigenvalues, right? So diagonal consists of the eigenvalues, and each eigenvalue corresponds in order with the eigenvector present in the P matrix. So we have the eigenvector, the first column of the P matrix constitutes the eigenvector associated with the eigenvalue 1. So we have 1 here. So second diagonal element, that is the second eigenvalue, which will correspond to the second column of the matrix P, which is an eigenvector corresponding to the eigenvalue 2. So we have 2 here, and analogously we have 2 here again. So this is your diagonal matrix. Right? So D is 1 2 2. One more thing which is very trivial to observe, and I hope you people have observed it by now, that if a matrix A is diagonalizable, if A is, let me just write it in a different color to mark its importance. Observe that if A is diagonalizable with to D, then D is consisting of the diagonal elements C1, C2 till some Cn, where each Ci is the eigenvalue of, right? So the diagonal form of a diagonalizable matrix actually consists of the eigenvalues along the diagonal, nothing else, right? That's a pretty trivial observation, right? So from here it's P times Q. So from here we observe that P inverse AP is equals to D, and this is the exact diagonal form, right? I hope it's pretty clear. Okay. So okay, yeah. So now let's come to the topic of annihilating polynomials. So I already have a lecture, a first lecture you might say, on annihilating polynomials on my playlist, where I had started the discussion of what annihilating polynomials are. So if I just give a quick recap, so it's basically, suppose T is a linear operator on a vector space V, where V is a vector space over a field F. Okay, then let Fx be a polynomial over the field F. Then F is said to annihilate T also said to be the annihilator of T, if ft, this operator is identically 0. That is, ft of any vector alpha is equals to 0. Okay, and we already know, we had discussed in the previous lecture only, that if fx, or rather this is pretty trivial, that if fx constitutes of this form, summation I is equals to 0 to some k ai x to the power I, then f of t is the linear operator of this form. So it's ai t to the power I equal to 0 to k, where t to the power 0 is considered to be the identity operator. Right? We have discussed it in the previous lecture. Okay. Okay. So a collection of all the polynomials over the field f which annihilate t, we can form a set of that called the annihilators of t. Okay, a set of all annihilating polynomials of t. So we can denote that as a n n t, let's say, defined as the set of all t annihilators. Okay, t annihilators. That is set of all polynomials which annihilate. Okay. Now this collection, it's obviously a subset of fx, right? A and t is a subset of fx. In fact, it is an ideal of fx. It is an ideal of fx. Now it's an ideal that's pretty easy to observe, because if you consider, let's say, two polynomials f1 and f2 from the annihilator set, then f1 of t is identically 0, f2 of t is identically 0, then what is f1 minus f2 of t for some alpha? So it's by definition it's f1 t of alpha minus f2 t of alpha, which is again 0 because each of these elements are 0. So that means f1 minus f2 will be in the annihilator of t, right? And it's an ideal because see, the field is a commutative ring. fx, the field of all polynomials, is also a commutative ring. So we no need to discuss about left or right ideals. We can simply discuss about the two-sided ideals. So let's let R be an element of fx, Rx be an element of fx, and small f be an element of the annihilator of t. Then what is Rf of t of alpha? So it's simply R of t of alpha times f of t of alpha, which is equals to 0. Similarly, fr will also equal 0, of t will also equal 0. So this will imply fr and rf both are in the annihilator of t. This comes with the usual multiplicative and additive operations of the ring, or I should say of the of the ring fx. We no need to focus on what type of ring it is. It's a ring. Right? More important fact is that fx is a principal ideal domain. If you have knowledge in ring theory, then you should know that fx is a principal ideal domain. That is, every ideal is a principal ideal. Every ideal is a principal ideal. And we can relate this to the fact that hence the annihilator of T has a unique monic generator, or I should say a least degree monic generator. But we can talk about that only if we are sure of the fact that there exists a finite degree annihilator of T. Right? Because if we have a finite degree annihilator of T, then we can consider the monic generator of the ideal ideal A n and T. Right? So let's come up with that. Okay. So what we do is if I consider an example of such an annihilating polynomial, it's the characteristic polynomial. Okay. Example: the characteristic polynomial of a linear operator T on a finite dimensional vector space V is an annihilating polynomial. Is an annihilating polynomial of T, and this is actually a theorem which is called the Cayley Hamilton's theorem. So it's the Cayley Hamilton's theorem. We will prove it in the next lecture. I thought of proving this in this lecture itself, but I think I won't be able to get enough time. But if I get, I'll obviously prove it. Whatever. Okay, yeah. So consider a finite dimensional vector space V over a field F. Let T be a linear operator on this vector space V, and let the dimension of V be n. Now we know, or rather I should assume for this moment, that if dimension of V is n and dimension of some other vector space is m, then the dimension of the collection of all linear transformations from V to W is given as n times m. Okay. So if I use this concept here, then I can say that the dimension of LVV, that the collection of all linear operators on V, is nothing but n into n, right? So it's n squared. Okay. Consider T to the power 0 to be identity, T squared to be T composed with T cubed to be T composed with T composed with T, and so on. Okay, so TR is composition of TR types. Okay. Now, obviously, since each T is a linear operator, so T composed with T is again a linear operator, right? Because V, if you consider V as a vector, then TV is again in V. So that implies TV is again in V, and since the inner TV is a linear operator, so it's so basically what happens? Suppose T of CV1 plus V2 is equals to C times TV1 plus TV2. But if I add a T here, so if I have a T here, so it's simply C times T squared V1 plus T squared V2, right? So inductively we can say that if T is a linear operator, every integral power of T is a linear operator, right? So therefore T to the power 0, and identity is also a linear operator, right? So T to the power 0, T squared, so on till some T to the power R are all in LVV, right? Are all in LVV. Now dimension of LVV is n squared. So if I consider any collection of elements from LVV with more number of elements than n squared, then it will obviously be a linearly dependent set, right? Because since dimension of LVV is n squared, so the maximum number of elements in a linearly independent set must be n squared. So if I consider any collection of elements from LVV which has more elements than n squared, then it will be linearly dependent, right? By the simple definition of what dimension is, right? Maximum number of elements in a linearly independent set can be n square. Therefore, this collection T0, T1, T squared, so on till T to the power n square is a linearly dependent set, as it contains n squared plus 1 elements. Right? So therefore, obviously there exists scalars all not zero. Therefore, there exists a0, a1 till an square, all not 0 in F such that summation ai e to the power I ranging from 0 to n squared is equal to 0. Therefore, fx is equals to I equals to 0 to n square. We just consider the polynomial considering these as the coefficients. So it's ai x to the power I is the annihilator of t. Right? Therefore, t has a finite degree annihilator. And this helps us in concluding the fact that the annihilator consists of a monic polynomial, monic generator, least degree monic generator. Right? Therefore, the annihilator of t generated by some tx where, so now we are considering obviously finite dimensional vector space because the previous proposition was about a finite dimensional vector space where p is a least degree monic polynomial such that, or rather I should say which satisfies the following properties, right? The following properties. So since it generates the annihilator of t, so obviously it's inside the annihilator of t. So p annihilates t. And number two, if q is a certain annihilator of t, then p must divide q. So this polynomial is called the minimal polynomial. P is called the minimal polynomial of the linear operator t. Okay. Obviously, we can have such a definition for an equivalent matrix as well, right? Because in case of a matrix, what's the annihilator of a matrix? So if q is a polynomial from fx and a is a matrix over f, then q of a equals 0 implies q annihilates a. Right? So it's analogous definition, q annihilates a. Therefore, you just consider all the polynomials which annihilate a, they form an ideal. You can, if a is a finite dimensional matrix, then you can obviously find a finite degree monic polynomial, okay, which generates the annihilator of t, I mean annihilator of a, by just you can just obviously visualize a as a matrix representation of some linear operator, because if a is a finite dimensional matrix, then obviously you can associate a linear operator with it. You do all the works of a linear operator and eventually come to the fact of a minimal polynomial of a matrix A, right? So that's pretty obvious, right? Okay. So what does a linear polynomial of a matrix basically does? So it annihilates the matrix, and if you consider any annihilator of the matrix, then P will divide that very annihilator, right? So P is a minimal polynomial of an n cross n matrix A if P is the least degree monic polynomial, if P is the least degree monic polynomial such that number 1, P annihilates A, and number 2, if Q annihilates A, then P divides Q, where Q comes from fx. Got it? Now in the annihilating polynomials part 1 video, I had discussed these in the annihilating polynomials part 1 video as well. In the annihilating, I'll give the link in the description. So in the annihilating polynomials part 1, I've discussed the fact that similar matrices have the same minimal polynomial. This video is in the same playlist as in which you are watching this one. That's the important topics on linear algebra. And I will also give the link to this video in the description. So there I have proved this fact that similar matrices have same minimal polynomial. A few simple observations regarding minimal polynomial is that we have also come up with the fact that similar matrices have the same characteristic polynomials. Similar matrices are having the same minimal polynomials. That's why, and so similar, the importance of similar matrices is pretty trivial, right? Because the whole concept of diagonalization is based on the concept of similar matrices. Furthermore, we had come up with, I just gave an example that the characteristic polynomial of a matrix is an annihilating polynomial of it, right? Therefore, the minimal polynomial must divide the characteristic polynomial as well. But we have a stronger statement. We come up with a theorem that let T be a linear operator on a finite dimensional vector space V over F. Let Px be the minimal polynomial of T, then P divides the characteristic polynomial of T and the roots of P are the characteristic values, that is the eigenvalues of T. So the strength of this statement is that we had previously encountered the fact that the eigenvalues can be viewed as roots of the characteristic polynomial. But now we can say that the roots of the that the eigenvalues of the linear operator are simply the roots of the minimal polynomial as well. So the minimal polynomial and the characteristic polynomial have the same roots, and both the roots are basically the eigenvalues of T. Right? So if you do not have the characteristic polynomial in your hand, but you can eventually come up with the minimal polynomial, then you can obviously find the eigenvalues by just considering the roots of the minimal polynomial. Okay. So let's prove this. Now the first statement is essentially trivial because we had already come up with an example that the characteristic polynomial annihilates the linear operator T, right? And we have stated that this is called the Cayley Hamilton theorem. We will prove it in the next lecture, or rather in this lecture I will try. Okay. So proof: since the characteristic polynomial of T annihilates T, therefore P divides it. P divides the, just write it in statement, P divides the characteristic polynomial of T, right? So it's obvious. Right? Now to show that P of C is equal to 0 implies C is a characteristic value of T. So now obviously if P is equals to C, if P of C equals to 0, then that implies we can write P of X as the linear polynomial X minus C times a polynomial Qx, such that degree of Q is obviously less than the degree of P, because the degree of Q comes down by 1 by extracting out this linear factor, right? It's pretty obvious. But then what is P of T? But then P of T is equal to, so it's T minus Ci times Q of T. Okay, and we know that P of T is 0. So since P of T is 0, because P is the minimal polynomial of T, therefore P minus Ci times Qi, P minus Ci times Qt is equal to 0 as well. Now, if T minus Ci is non-zero, then Q of T is 0, but degree of Q is less than degree of P. Thus, this contradicts the minimality of P, right? because by definition P is the least degree polynomial such that it annihilates T. But we are getting that Q is a polynomial which is annihilating T, but its degree is less than P. So it contradicts the minimality of P. Therefore, T minus Ci must be equal to 0. Right? Basically, since we are considering P of T, so we need to consider that with respect to some arbitrary vector alpha. So you can just consider it like this, right? So this, so Q of T is of some alpha equals to 0, right? For all alpha, you can consider them for all alpha in V, right? Or we don't need to mention this here because alpha is obviously arbitrary in each other. So that means T minus Ci of alpha is equals to 0, right? Or rather, we can talk about this. Since this happens for any alpha in V, right? Since this happens for any alpha in V, so we can consider this for some non-zero alpha in V, right? Because this happens for any alpha in V, so it will happen for all the non-zero elements. So this happens for alpha not equal to 0, but that means C is the eigenvalue of T, right? So that's the typical proof. Okay. Okay. Now, can we prove the converse, that if C is an eigenvalue, then it's a root of the minimal polynomial? Can we think of that? So let us just take that as well. So suppose C is an eigenvalue of T, then there exists a non-zero vector alpha in V such that T minus Ci times alpha of alpha basically is equals to 0. So that implies T of alpha is equals to Ci of alpha, but that implies P of T alpha is equals to P of C times alpha. So we have proved this fact, right? That if T of alpha is equals to some C times alpha, because C of I alpha is nothing but C alpha, right? Then that implies P of T of alpha is equals to P of C times alpha, right? So this happens, right? But P of T is equals to 0, so that implies P of C times alpha is equals to 0. Since alpha is non-zero as by assumption, therefore P of C is equals to 0. Therefore the eigenvalues are roots of the minimal polynomial, right? Got it? So let us come up with the next theorem, which is again very important in terms of diagonalization, and it's a pretty easy theorem. So let T be a diagonalizable operator on V over A. Okay, and dimension of V is some n which is finite. Right? Let C1, C2 till Cn, Ck be the distinct eigenvalues of T. Be the distinct eigenvalues of T. Then the minimal polynomial of T is of the form, so it's simply the product of linear factors consisting of each eigenvalue, each distinct eigenvalue, minus C2 till x minus C. Okay, that's the theorem. So obviously observe that the example which we have stated during the start of this lecture. So what was the example? Let me just view it once. So one second. Yeah. So the example was A is equals to 5 minus 6 minus 6 minus 1 4 2 and 3 minus 6 minus 4. We had shown that A is diagonalizable A is diagonalizable and the eigenvalues of A were 1 and distinct eigenvalues of A were 1 and 2. So the distinct eigenvalues of A were 1 and 2. So by the theorem we can say that the minimal polynomial of A is x minus 1 times x minus 2. And you can obviously prove the fact or observe the fact rather by just finding out that A minus I times A minus 2I will equal 0, and this is the least degree polynomial, or I should say the that this is the least degree polynomial such that this happens. What is A minus I? So A minus I was this matrix, right? So 4 minus 6 minus 6 minus 1 3 2, and we had 3 minus 6 minus 5, and A minus 2I was the following matrix. So 3 minus 6 minus 6 minus 1 to 2, 3 minus 6 minus 6. Now none of them are zero matrices, right? So this is not 0, this is not 0. The minimal polynomial will consist of the distinct eigenvalues. So obviously the minimal polynomial will have both of these factors, right? Both of these factors. So the minimal polynomial consists of some multiple product of these factors. So the minimal polynomial is of this form, right? So A minus I to the power some R1, A minus 2I to the power some R2, P of A, let's say, such that so R1 plus R2 must equal the dimension of it. So it must be 3. So obviously by this by this format we can obviously notice that A minus that R1 equal to R2 equals to 1 gives us the least degree polynomial Px of the form x minus c1 times x minus c2, where c1 and c2 are 1 and 2 respectively, such that P annihilates the matrix. Yeah, got it? The proof of this is fairly simple. Let's just consider the proof of this. Yeah. So proof, let Wi be the null space of T minus Cii. That is, Wi is the eigenspace of, or rather I should say associated with the eigenvalue Ci. Clear? So it's associated with the eigenvalue Ci. And since T is diagonalizable, therefore V can be written as the direct sum of, or rather I should not use the term direct sum, it can be written as a sum of these eigenspaces, right? W1 plus W2 till Wk. Since we have not yet discussed conceptually about the term direct sum, I won't be using that term. So V can be written as a sum of these eigenspaces. That's what we actually do. So therefore, if alpha is in V, there exists elements beta 1, beta 2 till beta k from W1, W2, Wk respectively, such that alpha can be written as beta 1 plus beta 2 and so on till beta k. Right. Okay. Now, so what was the statement? Let's see. So we need to check whether this is the minimal polynomial or not, right? The minimal polynomial or not. Now, obviously, if the way P is served here, if P annihilates T, then it must be the minimal polynomial, because the minimal polynomial must consist of all the distinct eigenvalues of T, and P is the least polynomial, least degree monic polynomial, which has all the distinct eigenvalues of T. So the minimal polynomial of this linear operator T has a degree either higher than P or it must be exactly equal to P, right? So we just need to prove, it suffices to show suffices to show P annihilates T as P is the least degree monic polynomial such that P of C equal to 0 if and only if C is an eigenvalue. C is an eigenvalue of, right. So just check that. Now what is P of T? By the way it is given. So it's of the form T minus C1i, T minus C2i, so on till T minus Cky, right? Where Px is given in the theorem only. So it's of the form x minus C1 times x minus C2 till x minus Ck. Have I written this statement in the theorem? I forgot. Yeah. Right? But that means Pt of alpha must be equal to 0, right? As each beta I is annihilated by Ci, since beta I is an eigen, or I should say by annihilated by the operator T minus Ci, I, as beta is an eigenvector, it's an eigenvector associated with the eigenvalues Ci, right? So since alpha is arbitrarily chosen from V, therefore P is the minimal polynomial of, okay, so let's end this lecture by giving a proof of the Cayley Hamilton's theorem. In the next lecture, we will discuss a few examples and a few properties of eigenvalues, and then we will be moving on to the concept of invariant subspaces. Okay. So the Cayley Hamilton theorem. So what does the Cayley Hamilton theorem typically say? So the very typical sense of the statement is that every matrix is annihilated by its characteristic polynomial. Okay. One second. Yeah, so as I was saying, that the basic statement of the Cayley Hamilton theorem is that every matrix is annihilated by its characteristic polynomial. So let me just write that in statement. Okay. So the statement is that let T be a linear operator on a finite dimensional vector space. On a finite dimensional vector space V over F, let Ftx denote the characteristic polynomial of T. Then Ft of T equals 0. So that is if Fa of x denote the characteristic polynomial of A, where A is a matrix over the field F, then F of A is equal to 0, 0 matrix, right? Here is the 0 operator, here is the 0 matrix. So you should be, beware of this fact. Right? I think I should have said aware of this fact. I'm very sorry. These lectures are actually not well prepared. I just discuss my thought processes through this lecture, having a few bit of notes obviously, but the proofs and the maximum observations which I come up with are, they deal with my thought processes. So I often just fumble around. Yeah, so the proof of this. So let A, so we prove this statement for a matrix, that will analogously prove it for a linear operator as well, right? Because to define the characteristic polynomial, we need to define a determinant. Right? For that, we require a matrix. So let A be an n cross n matrix over F, right? Over F, let characteristic polynomial of F, which is obviously determinant of xi minus. We consider this in this form. Okay. Now let's say fx, or I should say fa of x, to be of this form. So it's a0 plus a1x plus a2x square, and so on till. Then the previous lecture I discussed about the fact, I guess in the first lecture, that is eigenvalues and eigenvectors part 1, I discussed about the fact that the characteristic polynomial is a monic polynomial, right? So it's of the form a n minus 1 x to the power n minus 1 plus x to the power. Okay. We let bx be the adjoint. So it's classical matrix theory, right? It's adjoint of the matrix A minus xi, or rather I should use the term xi minus a. Right? It's xi minus a. Now obviously we form the adjoint matrix by calculating the cofactors of each element, and the cofactors of each element, they come up to be a polynomial of degree less than n. So eventually bx is a polynomial of degree less than n, right? Therefore bx is a, or rather I should use the term like this, that each element of bx is a polynomial of degree less than equal to n minus 1, right? Therefore each entry bx need not be a polynomial of degree less than equal to n minus 1. Each element of bx is a polynomial which consists of degree less than equal to n minus 1. Because suppose you have this matrix, let's say, for example, suppose you have 1 0 0 2, then what is the characteristic polynomial? So it's x minus 1 0 0 x minus 2. Then what is the adjoint of it? Or rather, let me take a three-dimensional example that will be more clear. Right? So let it be 1 0 0 0 2 2 0 3 1. Okay. So the characteristic polynomial is of this form, or rather I should say matrix xi minus a is of this form, right? So x minus 1 0 0 0 x minus 2 2 0 3 x minus, sorry, it's minus 2, it's minus 3, and this is x minus 1, right? So the adjoint matrix is formed like this, right? So the adjoint matrix consisting of the cofactors. So the determinant of x minus 2 minus 2 minus 3 x minus 1, then we have the cofactor of 0, right? So I'll put the signs later. So it's the cofactor of 2, it's 0 minus 2 0 x minus 1, then you have 0 x minus 2 0 minus 3, then you have here, so you cancel out these things, right? So it's 0 0 minus 3 x minus 1, and so on, right? I hope you have got what I am trying to say. So each element is of degree less than equal to 3, right? Each element of B is of degree less than equal to 3. So each entry Bij of the polynomial matrix Ba is of degree less than equal to n minus 1, where n is the dimension of it. Right? Further, or rather, let Bx, we give a representation of B. So Bx is will obviously, so it will be of this form. So it's x minus 1, x to the power n minus 1 times say Bn minus 1 plus x to the power n minus 2 times Bn minus 2 so on till x times b1 plus b0, right? This is an arbitrary representation of the polynomial matrix Px, right? So each entry bij of bx is a polynomial of in x of degree less than equal to minus 1, right? Now from classical matrix theory, I should say. From classical matrix theory, I should say, we know that A adjoint, or you can obviously consider this in any way, that we have A times A adjoint is equal to determinant of A times the identity matrix, where the identity matrix is of same dimension as A. We know this. Therefore, if I relate this to what we have here, so I can say xi minus A, this is the matrix with its adjoint, which is denoted as bx. This should be equal to determinant of xi minus A times the identity matrix I. Right? So I just need to expand this. Therefore, that implies to we have xi minus A. So bx is written as x to the power n minus 1 times the matrix bn minus 1 plus x to the power n minus 2 times bn minus 2, so on till xb1 plus b0. And on the right hand side we have the polynomial xi minus A, which is exactly the characteristic polynomial. So it's of the form x to the power n plus an minus 1 x to the power n minus 1 and so on till a1 x plus a0 times the identity matrix, right? So on either sides, if I compare the coefficients, so comparing the coefficients of each power of x, we have, so what is the coefficient of x to the power n? So what is the coefficient of x to the power n? So on either sides, I guess it's I, right? It's equal to I on either side. On either side, or I do not mention the term it's either side, in either side. Okay. So the coefficient of x to the power n equal to I means it's equal to I on either sides. So let this be 1. Let this be statement 1. Number 2, what is the coefficient of x to the power n minus 1? So the coefficient of x to the power n minus 1 on the left hand side, it's if you just multiply it, so it becomes minus a times b to the bn minus 1 plus bn minus 2. That is, you multiply this with this term and this term with this term, right? Plus bn minus 2, and on the right hand side it's an minus 1 times I. So it's statement number 2. So the coefficient of x to the power n minus 2, again if you relate both the sides, so it's coming out to be of the term minus a times bn minus 2 plus bn minus 3, which is equals to an minus 2I, right? So that be, so inductively we can proceed inductively, right? So we can proceed inductively. So we have the coefficient of x to the power 1 to be minus a times b1 plus b0, and on the right hand side it's a1 I, right? So suppose this is, so it's n minus 3, right? So it's n, so this is the nth equation, let's say, and then you have x to the power 0 as you have the coefficient as minus a b0 equals to a0 I, and let this be n plus 1 equation. Okay, clear? Now what we do is that we multiply a to the power n to the first statement, a to the power n minus 1 in the second statement, a to the power n minus 2 in the third statement, and so on till we have a in this very statement and I in this statement, right? And we add all of them up. If I add all of them up, you will notice that every term in the left hand side of this set of equalities, they cancel out. Okay, every alternate term cancels out, so the left hand side becomes completely 0, and on the right hand side we are left with this. So we have a to the power n plus a small a minus 1, a to the power n minus 1, and so on till a1, a plus a0 plus a0, I equals 0, 0 matrix. And but this is obviously nothing but fa of capital A. So this becomes right. Because if you have fx as the representation which we previously gave, so I'm just writing it up here, then fa, or rather I mean fx, so let me just, I'm not getting enough space, yeah, let me just discuss it here only. That is, obviously if fx is of this form, summation ai x to the power I equals to sum 1 to k, then f of a is of the form ai capital A to the power I with our usual matrix multiplication I equal to 1 to k, such that a to the power 0 is identity, right? So this is the thing we have applied here, right? So if a of capital equal to 0, and that's the end of the. Okay, so we end this lecture here. In the next lecture, we will be considering certain examples regarding the topics which we have yet covered, and then we will be exploring certain properties of eigenvalues and eigenvectors, and moving on to the concepts of invariant subspaces. So meet you guys in the next lecture.